So I have had some people on the live simulations have some weird difficulties getting in. It appears that Cengage is overloaded a little bit, so just keep trying. Usually if people try a couple times, the simulations don't seem as bad. The live labs, there seems to be a couple of issues with getting people in there. So be aware of that. Plan your time accordingly. Just if you wait until Sunday at 11 o'clock, it's probably going to be busy. So it's part of that piece. I am not, if it comes in and it's 11:01 or 12:01, I'm not going to be harsh about that. But if you're weeks and weeks behind, then that's going to be a little bigger of an issue. All right. So last week we kind of started talking about these IP, and so now we're going to get into a little more detail about how do those routers work. What are these protocols? In other words, those languages that we have. What are they? How do things route? How do things move around the internet? And so I have a couple of things we won't have necessarily time in here to do, and I can't really record a video of a video, but I will show you really briefly a couple of things, and we might point them out. There are a couple of videos about how does the internet work and some about some protocols that are in there. Those are there for you guys to look at and to use. They're not just eye candy. And we're going to try to get where we can show you the Wireshark. So last week, your assignment was, in the discussion board I believe it was, to install Wireshark. And a lot of people, for whatever reason, chose not to do that assignment. But this week, we're actually using that. So I hate to be the person that say, gosh darn it, I hate you, go back and do it, but you need to go back and do that. Because it's hard to do the assignment. They're designed that way and they stack up. You need Wireshark to be able to do some of the assignments this week. And it's one of the most widely used tools, so having some knowledge and some exposure to that isn't necessarily a bad thing. So this is where we start looking at those pieces a little more in detail. And it gets a little ugly. I'm the first to tell you that some of this is ugly, and part of it is the reality that our computer sees nothing but zeros and ones. And so when I send data out, all it is a string of zeros and ones. How does that receiving computer know anything what those zeros and ones are? And so this is where we start to make those details about how this is going to work. So this chart here is probably the most useful one we have trying to understand that. And so one of the things we have to, as we start at the top, is as we move down, that payload gets things added to it and then becomes the subsequent payload. So at the application layer, that payload slides down, and at the transport layer, we add a header to it. In other words, another string of zeros and ones. When it moves down to the next layer, the data is really both the header from the layer above and the original payload. And finally, when we get to the bottom layer here, our data link layer, there is a header and a trailer that are added. All of this is payload, but a lot of it is the data that's moved down. And we're going to look at what moves down and what that original payload is. And remember, none of this can be anything but zeros and ones. And if I just hand you a string of zeros and ones, you don't know what they are. When that CD player makes music, you don't know what those zeros and ones are unless it gets interpreted into a song for you. So we're going to look at some of these in a lot more detail in the next couple of days. So this week has some tough stuff. So this says, well, this goes here, it goes here. It's really the same thing as what we're trying to explain here. And I think visually, this makes more sense. So we have our payload, becomes a segment, becomes a packet, and finally becomes a frame. And we're going to look at what those details are in there. And we also need to know what those IP addresses and those ports are. Because we need both of those to make a connection. So in our lab, I'll show you an example of those right now. So you said, when do I ever use these things? So when I go to a browser, so if everyone will go to a browser of some sort. So in here, if you will type in the following number, 192.168.180.5, and if I stop, by default, it's going to say, oh, you want port 80, because we know that most of the video traffic and web traffic is on port 80. But I don't. I want you to put a colon, and I want you to put 81. And that actually makes it a socket. When I have an IP address and a port number, it becomes a socket. And when I hit enter, oh, I am somewhere different. So it's pretty tight. It's remote, remote. So if you type remote for the username, remote for the password, you are now on our tentative server for a couple of video cameras. So if you look up to your left, those of you in there, there's a video camera in the ceiling. There's one actually in the other room also. And so this is a viewer. It lives at 192.168.180.5 colon 81. So it goes to a specific port. So instead of using port 80, we used port 81 just to say that we're moving to that particular port. So the reason we're putting these in and trying to do this is a couple of things. One, a lot of times this lab is left unsecured and we've had some issues. So, hey, now we can actually record the lab, and we're doing so. And B, we have these split classrooms that are big enough, especially the 101 classes, that they're in this room, and you'll see there also is a lab for over next door in 203. And so we can actually, what our plan is, that TV, we're going to run a web browser, and they're going to have that up on the screen. We actually have 2 more cameras to put in, and we haven't done it yet. And they'll be able to see everything from this room and everything in that room all at one time on a fairly large monitor. So that's what they're for, kind of a twofold purpose. But that's an example of that IP address and a port. And so we're going to look at what that port does here in just a second. All right. So now you know how to get into the web camera system at any time, or at least the viewing of the web camera. So each layer has some special things that are going to happen at it, or tend to be. Now, some of this is a little bit in flux. I will say it is not an absolute that switches are layer 2, routers are layer 3, firewalls are layer 4. Because we are adding more, I would say intelligence, but it's really more processing power to some of these devices, we now have switches that are actually, we call them level 3 or layer 3 switches that can do some of the tasks of a router. So we're moving some of these functions up and out, and we now have firewalls that are, we call them layer 7 firewalls, that are very skillful and very processing intensive and able to handle some of that data. So typically this is the way it is. We look at a switch as layer 2, router layer 3, firewall layer 4. And it has to do with this and what they affect. So layer switches typically need all of this, the frame, to be able to work. The router actually adds that data to the frame so that it can be routed. So you're going to see as we start looking at these packets, we have to understand a little bit about how they work. So we call it the TCP/IP. And TCP, Transport Control Protocol, is really a form of a language or an algorithm that works, and it does a couple of things in there. And one of them it does is it's called connection orientated. And connection orientated means everything it sends out has to get an acknowledgement back. So every message I send out, if I didn't have every student in here say, aye, aye, Captain, I would say it again until you guys got the message. So there's an acknowledgement that happens on everything that goes out. We call that, you'll see that we'll see the term, you'll see it called a three-way handshake. Because before I ever send data, I send out a message and saying, hey, I want to send data, I want to send an acknowledgement. You send an acknowledgement back, I send data, and then you send an acknowledgement. So it has some steps to it. It is not free in terms of resources. It takes some resources to send data about every package. It also does something called sequencing. So you'll see that that works in hand with that handshake. It sends a sequence number with everything so that we can reassemble it in the correct order. Those packets don't always get there in the correct order. We need to put them in the correct order. It also has something called checksums in here. And a checksum is nothing more than a mathematical operation to say, hey, I think this is what it should be. So if we have a checksum on your checking account balance, it would be like a no or go thing. So above $100, below $100. It's just a real quick go or no go. Well, the checksum's a little more complicated. It takes a mathematical operation and sends out that number back and says it should be around this based on this mathematical operation. Great. I know that that data did not get disrupted. Remember, we're sending out only zeros and ones. If we miss a couple of those ones or a couple of zeros or something gets mismangled, that checksum is our way to see is that value correct? Did that picture get sent correctly? And then the other thing that it does that's kind of interesting is it does something called flow control. So how fast can I send data? How fast can I receive data? So we have different speed abilities. Some computers, much faster. They have a faster network card. You have a faster network that you're on. You can send data faster. And so at some point you have to have some way for that computer that's receiving data to go, whoa, no, I can't handle any more. My buffer's full. Any more data you send to me is going to get lost. And we don't want that. We want to make sure that data gets received. So we need to look at this data and what it looks like. So remember, TCP is in that transport layer. It gets a header. And so we're going to look at what this header looks like. So this chart is you want to think about it as bits, 0 and 1s only. And each time we go from left to right, it's 32 bits. 32 bits, 32 zeros and ones. To make it so we don't have to take up 17 screens wide, we stack those. And so you could say this is 1, 2, 3, 4, 5, 6 times 32 bits at the front being added. And so the very first thing it adds is it says source port, where am I coming from? Destination port, where am I going? Yeah. All right. So it then also adds a sequence number. That sequence number is 32 bits. It adds an acknowledgement number. It actually adds a value here that says, how long is this header? So notice here, this padding, that's not set in stone. Sometimes we pad that out so the entire frame is a specific length. So it's got to say, how long is this header? How many zeros and ones? That's all we have, is that ability to pull out a chunk of it. So there's some markers in here. Here's our checksum. So in other words, it calculates and says, all right, it should be equivalent to this. There's other pieces, some options. And then finally our data. So this is all added on top of our data. So maybe this is a music song. Some kind of new artist has produced a new song. To send it out, we have to add this piece in. But what's missing in there that we've already talked about a lot? What do we typically say has 4 fields in it? An IP address. There's no IP address in here. TCP is only sending out based on ports. Oh, wait a minute here. So, sequence number. This is what we call non-routable. It can't leave our local network because it doesn't know where to go. It doesn't have any IP addressing on it yet. But I can sure send it from one computer to another in our network using TCP. But TCP requires that ability to make that handshake, and it sends that sequence numbers and acknowledgement numbers back. So this is that 3-step. So it sends what's called a sync packet. So it says, hey, I want to make a connection with you. The computer that then responds and says, okay. It also sends a sync packet and an acknowledgement and says, all right, I acknowledge, I see your packet, I'm sending you a synchronization value. And then we get a connection back that says, all right, I acknowledge. That sounds pretty interesting. And then those sequence numbers, once they're generated, they're going to increase every time we send a new packet. So those sequence numbers really do go up every time. So maybe it makes more sense if we look at it this way. So computer A says, I want to talk to computer B. And it sends a sequence number. So if we look at that number, 937015558, whatever, and I don't have an acknowledgement number. That's blank because I'm not sending an acknowledgement. The only thing I'm sending, I set a flag for a sync. Computer B then says, all right, I got this message from computer A, and so I'm going to send it back a sequence number. And those are usually randomly generated to start with inside of your computer. Its acknowledgement number, though, take a look at that. Does that number look kind of familiar in there? Yeah, it's your sequence number plus 1. So it sends back that acknowledgement number, and it set 2 flags. It said, yes, I'm acknowledging, and I want to sync with you also. So both of them have to be in agreement. And then so computer A then says, all right, I've got to send an acknowledgement that I got your message. And it sends it. Its sequence number then, notice, goes up by 1, which just in this case is the same as your acknowledgement number. And then it sends this acknowledgement number, which is your sequence number plus 1. So we kind of have a running tally, if you want to think about it that way, between the two of them. We have not sent any data yet. That is just to start the process. It's called the 3-way handshake. So computer A says, I want to send data to you. Computer B says, I got that message, and I want to send data to you. And computer A says, I'm going to acknowledge that. Every message we send has to have an acknowledgement. If we don't get an acknowledgement, I'm going to send that data again. And I'm going to send it again. And I'm going to send it again until I get an acknowledgement or I time out. It's called connection orientated. I'm making sure that that packet gets there to the best of my ability. Connection orientated. Well, there's another way we can send packets. And this way has a couple of advantages or a couple of disadvantages, depending on how you want to look at it. Doesn't have a 3-way handshake to begin with. It doesn't carry delivery, so there's no guarantee that what got sent out is what you received. There's very little error checking. In other words, it really just blasts out data. So where does this fit? Things like audio, video, live. Because if I miss one packet sending out data, you're not going to notice it. In a video, it might be a little fuzz in one little spot. So it has less overhead. So if I look at what it's adding on there, it says, here's where I'm coming from, here's where I'm going to go, here's how long I am. It does have a checksum, but we don't really do much with it. because that checksum on the receiving end, if we get it, we get it. If it doesn't seem right, we just drop the packet. We just ignore it. And then there's our data. Look at the size difference. And so that size difference is part of the reason we want to use it for things. So here we have 6 times 32 bits, plus at the beginning of that message we've got to do that handshake, whereas UDP, we just send out data. We start blasting it out. Live sound might be okay. If I'm sending bank account information about everybody's checking account balances, might not be the way to send data. So they both have a purpose, both TCP and UDP. So when I set up something like a Zoom, they use a lot of UDP datagrams because I don't have to make all that connection. I don't have as much overhead. I can just blast data out. When speed is more important than accuracy, I can use UDP. When accuracy is more important than speed, I use TCP. So, same way to send the same information, because it's still going to a source port or a destination. So, IP then says, all right, our next layer says IP goes, all right, I'm going to add now an address, an IP address to that. So the layer called IP adds an IP address. Not really necessarily shocking in that case, if you think about it that way. So IC or IP enables TCP to go more than one network. Couple of things. It's unreliable. In other words, there isn't connection orientated. It relies on TCP inside of it to make sure that that data gets sent correctly. So IP depends on that TCP if it needs to be connection orientated. So our previous packet, so here's that datagram, and it's already got, if it's a TCP, it's got 6 by 32 bits in it already of a header. We now buried that header in our data for the next layer, for this IP datagram. And this IP datagram then has a couple of interesting pieces in it. So once again, in this case, the header itself is 6 by 32 bits. Total length is in there, so it says how many zeros and ones are in this entire group. And that's the only way we know when to stop. There's not a number 3 that says, hey, get all the zeros and ones until we hit number 3. There's no way to do that. All I can do is count the number of zeros and ones and go, oh, it said there should be 754 of them. Chop. So it's got a couple of pieces that you're going to see in here. Source IP, where it's coming from, and where it's going. So now we've added that IP address. Inside of here are those ports. So now we've added some more data. A couple of other things you've probably seen. You see that TTL. We talked about that a little bit. Time to live. That's where it hangs out. So this is where we would kill off this IP datagram if that TTL reached 0. So it looks very similar in IPv6, but because it's much longer, there's a couple pieces taken out. So we have to know if we're sending IPv6 or IPv4. So there's an IPv6, kind of similar, except it's much longer. And part of the reason it's longer is those source and destination addresses, instead of being 32 bits, are 128 bits. So it takes up a lot more header. So this is maybe a reason some people think IPv6 takes longer or it's slower. You're adding to each packet more stuff, more header. But it's actually a little better in the respect of it has less items in there. So we have a traffic class. In other words, we can put quality of service on. So we might say, hey, this is phone traffic. It's got to have quality of service over your email, for example. So we separate them that way. It also has some hop limits, which is very similar to the TTL. So a lot of these are very analogous. We're going to mostly deal with IPv4. So we have another protocol, another language or another piece we need to think about, a set of rules. So ICMP, Internet Control Messaging Protocol. So this is very useful for us. A couple of things we've done. We've already seen that TTL packet. When it dies, it says, I'm going to send back to the sender a message saying your packet died. And that's the basis for that trace route that we did. So when data doesn't reach its destination or it fails or there's network congestion, that's how we can actually reroute in some cases. And it doesn't directly reroute everything, so we have to have some other pieces in place. On 6 networks, it's really the same thing, structured a little different. But if we understand it on IPv6, we understand IP4 pretty much. So this is a packet for ICMP. It's pretty short. It really says, oh, what type, what's my code? It has that checksum again. And then says, oh yeah, in 32 times 2 or 64 bits, it's going to send back a lot of data. So the type, the code, so the subtype, so whether it's did the TTL die, whatever it was. What it does have for this data, though, it takes that IP header and takes portions of that data. So it grabs a piece of that packet that dies or isn't being able to route and says, here, so you can verify that it really is. This is your packet. How did it die? The American Retired Association of People, or Address Resolution Protocol, one of the two. So your computer's really dumb. ARP is one thing we use to help that computer be less dumb. So I don't know where I'm sending my packet. When I and I say, oh, I'm going to send it somewhere, I need a map to get there. And so ARP maps those IP addresses of our computer to a MAC address, but on the next network over, so that we can figure out where that packet actually gets sent. The only thing that is really on your computer and static all the time is that MAC address. And so I need to figure out how I get data over to that MAC address. And so ARP says, this is the MAC address, this is the IP address. This is only on our local or our LAN. ARP also does something called broadcasting, and we'll see some examples of it here when we fire up Wireshark. Broadcasting says, I'm going to fire out to every computer on my network. I'm going to broadcast. So when I'm out and I put seed on the ground and I broadcast it, I throw it everywhere. That's the same way we're doing with this. So we're adding more network traffic by using ARP, but it gets us some information we need to know. So here, for example, IP address, that hardware MAC address, and what type of address it is. Is that a static IP? Is it a dynamic? So you build up this ARP table. You send out data, and so you're really asking, in most cases, and you'll see what it actually looks like. It really says, who is this number, this IP address? So you can actually see what your computer sees. and you can use the ARP command. You can see the values of those computers that you can directly talk to because you know their MAC addresses and their IP addresses. So, ARP-A, I'm not going to do that because I want to get to the Wireshark as quickly as possible, but it would look something like that. So if I did an ARP-A, I'm going to get a list of internet addresses and physical addresses. So we will see what some of those are. Some of them are going to look a little odd. So at the top, you're going to have the ones you think you have, and then all of a sudden you get these ones at the bottom, and they're going to have strange addresses, and there's some broadcast addresses probably on this network. And then finally we get to the Ethernet layer. And that Ethernet layer is really what makes this whole thing work because it adds a header and a trailer. So it encapsulates that data we have. And remember that data also includes 2 layers of headers. This is how all of these computers work together because we can run Ethernet on all different types of media. So it can be on fiber, it can be on wired, it can be wireless. There's more than one standard. We have somewhat standardized on Ethernet 2 as the most common. And it does. It puts a header and a trailer on everything. So it puts we call it, sometimes you call it a frame. So in other words, it says, all right, here I have a preamble, my destination, my source, the type, what type of Ethernet I'm on. This is all those pieces we've had before, and then it adds a frame checking sequence at the end. So it's got a header and it's got a trailer. This also allows us to set some size limits of how big we are. So the header and the trailer, so there's only 18 bytes. Now, when I say byte, that's different than bits, right? There's 8 bits in every byte. So we switched talking about from bits to bytes. Bytes are useful. Bits are just zeros and ones. So bytes are now useful. And we end up with a number here called maximum transmission unit or size. Most of the time in our networking, we're only able to send 1,500 bytes total. So that includes you're losing 18 for that frame, and then that inside piece has the rest of that. So about 1,500 bytes. That's about, if you put characters on a page, that's about 1 page typewritten. That's it. That's what we send out. So when we go in the internet, that's about all we can do in terms of size. So we have to break these down into small enough portions that we can send it in that MTU or 1,500 bytes. Now, there are some special cases internal. So internally, sometimes we can actually use what are called jumbo frames, so we can send more data. Every time we break it up, we're adding more overhead. We've got a header, we've got a trailer, and there's CPU time to put all these chunks back together. So inside of our networks, we can use these jumbo frames, and we can have a little bit better efficiency. In other words, less overhead, less CPU time internally. Doesn't work external. So once we hit that demarc point and we got to send out onto the internet, we're back to that 1,500 mark. So the entire world operates on these little bitty chunks of data the size of one notebook page. So when I send out videos on Zoom, it's sending them out in chunks the size of a notebook. And it has to send a lot of them out there. A lot of them out there. All right, let's talk about routers really carefully, and then we're going to start with our Wireshark, and we're going to take a look at Wireshark. So a router really says, I have two different networks and I need to connect them. I need to figure out how I can send data from one side of my network to the other network. Typically they connect those, and they're layer 3 or layer 4 devices. And it also says I have to determine the best path. And if that path is blocked and I can't get data, I have to see if there's another path that it can get from. So routers can be very powerful. So something like this, a big Blade server, or this is a Juniper Networks. So you're talking hundreds to tens of thousands, or then you get the $100 device for your house. And they all do the same thing. This one has abilities that the other two don't. This one has abilities that this one doesn't. So the scalability of those routers becomes important. How much data they can route, what kind of rules you can implement, and where they can go. There really are reasons why the $100 router isn't the best choice for a business. When we first built this lab, and this is many years ago, so 2011, we thought, well, you know what? Just for giggles, let's see what happens if we hang a home router. And so we bought a home router, just a wired, I think it was probably $85, $90 back at the time, router in here, and see what happens. And in here we had 34 computers at that time running off of that router. And it failed miserably. It could not handle that amount of traffic. But yet every day we see businesses that are in the same way, and they don't understand what's going on, why they're losing packets, why their internet's slow. But I paid for the biggest internet package. Yeah, your internet package you bought is 100 megs per second. Your router's handling 10 megs per second at most and falling on its face. So, but getting them to spend money seems to be sometimes hard. But that's the kind of the scale of routers. You can spend as much money on a router as you want to. So what other things can it do? So it can actually filter. In other words, drop traffic, prevent some traffic. How do I support traffic both coming in? One of the things we see a lot is this idea now of these VPNs during this pandemic. In other words, I tunnel traffic into the inside of my network, and that's done with some kind of a router. So you've already seen when we looked at our router for this room, we do some port forwarding. And when we get into the commercial side, so for a business, they'll typically have two power supplies. We know the most common thing to fail is a power supply or a fan, so they will have redundant fans, an extra power supply in a lot of cases. They're hooked up to battery backup systems, so if the power goes out, they're still able to run. If a fan dies, a lot of times we can replace a fan while it's still running. You can't do that on your home system. The power supplies we can replace. One of the things we see now is we get those logging reports. So now we can see every spot you've been on the internet. So in this router back here, I can turn on logging, and I can see every place you guys have been at every computer, where you've been, how long you've been, what data you pulled, what files you downloaded, what information you got. Sometimes that should scare people. When you do it on a company side, you can see the same thing. So down in the admin building, they can actually pull up, if they had the time, which they don't, hopefully, but they can actually look and see where all the data is coming from on the campus. It can usually also assign some rules that says, oh, I need to limit a little bit of the bandwidth at Delzell and a little bit at Morgan so that we have enough bandwidth in the administration building that we can send reports. So we get some ability to do those kinds of things also. We break them into some categories. So you'll call an interior one a core router, You might see something called an edge router. So out here at the edge of our network, at the edge of Peru, we might call that an edge router. And then these routers that the internet service providers have, typically we would call them an exterior router. They're not really used interior-wise anywhere. They're used to route the big chunks of network traffic that go from one spot to another. So we'll see different terms. Now, strictly speaking, a lot of times we use the same router models, and it's really just the rules we put into them or the programming that we put into those to have them do different things. They're based on how much they can process. So they're expensive. It is not uncommon to spend thousands of dollars on a router for a fairly small business. In here we have now about 50 some devices behind a router. And the reality is, in some cases, depending on what we turn on in terms of filtering and looking at it, that router needs to be upgraded. The next upgrade from the router we have in here is about $1,500. I haven't figured out how to pay for that one yet. So the next router upgrade will have some additional features, or we might break it apart a little bit differently. So routers are kind of the, if you want to call them, the traffic cops of the organization. And what we're seeing now in a lot of cases then is layer 3 switches or layer 4 switches. So layer 3, layer 4 switches include some of that routing functions, and they're specialized enough that we put different features on them. So the new switches that they put in these buildings here, for example, have some ability to take traffic no matter what it is and route it on the appropriate VLAN. And we haven't really talked a lot about VLANs. When I look at something like a 48-port switch, I can go on to Amazon and find a 48-port switch for a couple $100. It's not going to be a layer 3 or layer 4 and able to handle that kind of content. So there really is a cost. A good layer 3 or 4 switch, you're probably talking $5,000 to $6,000 or more for a 48-port switch. Networking in the enterprise level or the business level is not cheap. And you don't want to go cheap. Going cheap can lead to a lot of issues. You spend more time trying to chase after issues. All right, so I'm going to leave us at routing tables. But what I want to do is I want to look at week 6. So week 6 has a couple of pieces in it. So there's a preview, there's our reinforced, so key terms. And again, there's a lot of terms, so I encourage you to do it. Crossword puzzle, if you can get it to load. Again, for whatever reason, those seem to be a little hard to do. The reading for this week, and then we have a couple of simulations. There is a review. This doesn't generate points, it's just our PowerPoints, much like I looked at. There is a quiz. I have a couple of videos that might be very handy for you. If you just want to download the PowerPoint for this chapter, it's here. But what I want to look at is this, Lab Manual 4-2. This is the first time I've said, hey, let's do a lab manual. It's not the live labs, it's not the lab simulation. What this one does, let's see if I can get it to open. Maybe I already have it open. Oh, I do. All right. So this one says we're going to examine those frames, and we're going to do it inside of Wireshark. So it says we should take about 45 minutes. We don't have quite that much time in here, but we can get a start and try to look at it. So here's that Ethernet 2 frame again. And notice we went from bits to bytes. So this is really, if I had 8 bytes, and I want to know how many bits that is, what's 8 times 8 is 64 plus another 6 plus. So you could figure that out to make those apples to apples. But this is what we want to look at so we can start to find some information in here. So we're going to have had Wireshark installed, which again was one of that previous assignment. And what we're going to look at is some specific things in Wireshark. So hopefully this, so down here it says it's got a 7-byte preamble and a 1-byte start of frame delimitator. So in other words, at the beginning is 1 bit that says, hey, we're starting, and then there's some additional information. A 14-byte header, so 6 plus 6 plus 2. So destination MAC address, source MAC address, the frame type, so it says, all right, I'm Ethernet 2. The payload, so again, we're between 46 and 1,500 bytes. If it's not long enough, so maybe we sent a message that just said no in a chat messenger, and that's the only thing it had was 2 bytes, it's going to add information to get it long enough to send. And then at the end, this is a frame checking sequence, and it uses something called CRC. So again, it's a mathematical operation. Takes this entire thing, chews on it a little bit, and puts out a 4-byte number that's equivalent to the entire frame. And as long as that frame isn't altered, at the other end I do the same mathematical operation and I get the same value. So, little disclaimer. So Wireshark or most softwares can't capture the preamble and the frame checking sequence. I can't grab this piece and see what it is very easily. There are hardware devices that do that. All right, so I'm going to follow these and see if we can get through part of this together in class. Is anybody that's sitting at a computer not have Wireshark installed? A couple of you. All right, so I'm going to go through that. So if you have Wireshark up and running and installed, sit there and look pretty for a minute. So I'm going to go to Wireshark. So I'm just going to type Wireshark. And I'm going to go to this page like this. Should look like a shark. And I'm going to click Download. There are various versions of installers. So if I have a Mac, I'm going to grab this Mac version. If I want to do a portable app, which you can actually run off a flash drive, it's kind of handy sometimes. There's a portable one, but the one I'm going to hit is it'll be recommended for your computer, which version is probably the best. And it says, all right, the Windows installer here for 64-bit. So I'm going to click to download it. Shouldn't take but a couple seconds to download. And then I'm going to run that file. It will pop the UAC up and say, do you really want to install this? And so in this case, it's going to say, hey, it's already installed. Would you like to uninstall it first? Sure, let's see how badly we can corrupt Windows Registry. So I'm going to uninstall it and reinstall it. And so it pops up in the other window. Makes life more fun to record. All right, I agree to all that. I'm not going to change any of this. I'm going to use the defaults. So I'm going to click Next. I'm not changing any of these for now. I'm just going to click Next. Where it's going to go, Program Files. Yep, going to install it. This, if I do not have a new version, so in this case, the version of NPCap, so that's the actual capture piece of this behind the scenes. There's not a lot of versioning difference, so I'll click Next anyway. It's going to uninstall the old version. So this one may be one that some of you need to add when you run it. It does sometimes cause hiccups. If you are using a USB adapter to get on the internet, and most of you are probably like, I don't even know what you're talking about. If you have to plug in a USB cable that's got a couple of antennas, maybe you needed longer range, maybe your internal wireless died, or you've got a desktop and you're plugging in that, you might want to install the USB P cap. I do this on my laptop. I use that one because my laptop doesn't have a hardwired Ethernet connection. It only has wireless. I use a little USB adapter so that I can take my laptop and actually get on a wired network. I do that because sometimes I do these weird things like Wireshark, and it doesn't work very well if I don't have the ability to do that. So I have a really thin notebook, and now I've got another 5 pounds worth of adapters and things, so I'm not really sure I saved a whole lot, quite frankly, in the end result. All right, so I'm going to install this. It'll take a little bit. Probably faster on everybody else's computer out there other than mine, because I actually weirdly have one of the slower ones. And I'm transcoding a video to upload right now at the same time. So this poor computer is probably saying, stop that. All right, I get an agreement in here. So I'm just going to click install and not grab any. So now it's going to change out for the new capture piece. Next, finish. All right. I don't want to reboot because I'm recording, so I'm going to see if this is actually going to work. That may be incorrect, but I am now going to start Wireshark. So I'm just going to click the Windows button and type Wireshark, and the app will actually hopefully start. So one of the things to notice on this screen, I don't know if you guys can see it up there, it's kind of small, is up here it says these are all my connections. And we've got some virtual connections, and this one's got some other weird things. But what you'll notice is this one actually has traffic. Notice it's got like the little heartbeat going on. This is that adapter if we needed to loop back. And it gives us some similar data, but if we have one that's getting traffic, that's the one we're going to want to select right there. So I'm going to go back to my instructions. I'm getting ahead of myself here a little bit. All right, so we've installed Wireshark. It seems to open. All right, so click capture and click start. Okay. So I'm going to go back to it. And over here, hang on, let me make this half the size so I can actually see it on this monitor. So here's the short piece. So this little shark fin here, if I just click it, I start capturing data packets. So our book is, we're going to do something very specific, but I just want to show you what's happening right now. Now I am uploading a ton of data, so this is probably a bad computer to show this on right now. But I'm going to click stop. And so I captured some data over, I don't even know how many seconds. And notice I grabbed 287 packets in that. So we're going to go back and look at some of this and follow the instructions. But I just wanted to see what was going to happen when I did that. And so you'll notice I said something about the ARP packets right here. So in this particular case, let me see if I can change it to trunk. And notice if I can change these by any of the top, I can rearrange them. So in this case, it says, here's a broadcast packet which went to everything on the network, and it's ARP, and so it's asking who has 192.168.180.22. Tell 192.168.180.5. So the server doesn't know who's got 22. The server asks again. The server asks again. So any guess what 22 might have been? I'll give you a hint because it's not up here in front anymore. 22 was the printer back here. So our server is very concerned that it can't find that printer. And this is all traffic. And in fact, a lot of it is generated by the server back there saying, who has this address? Who has this address? Here's the really weird part. That server is the one that assigns most of those addresses. Networking has some holes in it, I think. And we're going to discover some of those. But here we have one that says, who has .40? Tell 168.180.242. Tell 242. Well, that intrigues me. I see that 242 up there a lot. So I'm going to open up another tab. I'm going to see if I can get a response out of it and figure out what that is. I'm just kind of curious. I'm going to guess it's not going to connect. And it's not going to easily. But when it's asking for that, I can see a little bit of information. It's one of these computers in here with a gigabyte motherboard, keeps asking. That's all the traffic just to try to find out information about the network. So I'm going to go back here, and if I click Start again, it's going to say, do you want to save any? Well, I don't really want to save anything, so I'm going to cancel for now because I want to get my instructions ready to go and see if I can start this without having a whole lot of problems. So I need a command line prompt, it looks like. And we're going to do an NS lookup. So before we even run Wireshark with it, we're going to make sure that works. So NS lookup. So it's got a couple of addresses. So 3, 52, 54. So it's changed since this address. Here's another instruction, ipconfig all, which we've used. Enter a ping of the Cengage address. And then while we're doing this, we're going to look at Wireshark. So let me go to Wireshark and see if I can put it on half the screen, which I think I have there. And let me come over here to this and see if we can do this all kind of at the same time. I might move my directions off screen so I can see what I'm doing. I'd like to say my memory is great, but I'm already confused. All right. So now I have two windows open that we can all see. So my first instruction was to do, got to scroll back down here. So we're going to do the NS lookup. So I'm going to go ahead and do this, do my up arrow key, and I'm going to click Start, which will wipe out everything we have, and I'm going to click Continue without saving. Now I'm doing what I'm asked here, and I'm going to hit Enter. All right, now I'm going to do an ipconfig/all. Enter the command ping, and I'm just going to do -t, and I'm going to let it run for a little bit. So as they're now hosted at Amazon Web Services, they're not going to let us get traffic in. And it says, all right, look at the Wireshark window. When the total number of frames is greater than 10, stop. Well, we have clearly more than that. And so I think we're at, on the left, we're at packet 352. So I want to figure out what my source address is. So I'm going to scroll this over a little bit. And I can highlight by column. Well, I happen to know that the address of this computer is 103. So I scrolled up until I found one that says 103. So that says this is a packet that this computer sent out. Here, let me cancel that real quick. So in that amount of time, that computer sent out from here to wherever it is. So now we've got some packets, and we can actually look and start figuring out. So what I'd like to do is see if we can find one that says an ICMP packet. So protocol and 103. So I'm not sure I will see one since it got rejected. Let me see if I even see one at all in here. Oh, I do. ICMP, there's one from here. So from this computer, it tried to go to Cengage at 54, and it says, hey, it's a ping request. So I can actually see what that packet looks like down here. So we know that it's frame 266. Altogether, it was 74 bytes. So it's between 46 and 1500. And it says, here's my interface, the type, and notice these all pop out. So I can get additional information about each one. So if I scroll down here, it'll tell me when it was sent, the frame number, the frame length, the protocols in the frame. I can open this up, and I can see that in this case, its destination, it hit the Ubiquiti, which is actually our router. Its source, well, that's motherboard is a BioStar motherboard, so that's the Ethernet card on there. It says it's a IPv4, and so here all those fields that we had in there, we can actually see what they are. So time to live is set at 128. It has an offset of 0. It's got an identification, a checksum, a source, and a destination. So the Internet Message Control Protocol says it was a ping request. Checksum says it was good when it sent out. It has a sequence number. And then says, nope, it never did get a response. So if we sent that to a different server that actually responded, we would see something different. So hopefully this will give you a start on this assignment. So in the middle pane, note the frame is divided into 4 parts. Click the right arrow next to Ethernet 2 to expand it. So that would be these parts here that I expanded. So 1, 2, 3, 4. And so it says, click the right arrow next to Ethernet 2. So Ethernet 2, we would open it up. And I can even move this around this way. So I can make this bigger, and I can see what's happening. So this is what we call a frame capture or packet capture program. So everything that this computer sends out and receives, I just captured. There are different types of protocols, and so we're going to use this a lot, but I want you to get familiar with it here. So what is a source address? Is the source address an IP address or a MAC address? Well, let me look. The destination, so where it's going, is that an IP address or is it a MAC address? So what do we think? We see that it's got a destination here. Is that a MAC address or is that an IP address? How would I tell the difference? What kind of numbers is that in that destination? Is that binary? What kind of numbers is that? And we can see how many groups there are. So if you don't know, you can always go find something like MAC address format. And if I do, notice it says, all right, it's 12 hexadecimal numbers, which are represented by, all right, so let's go look here. So there's 1, 2, 3, 4, 5, 6 times 2, or 12 values in there in hexadecimal. So is that a MAC address or is that an IP address? It's going to be a MAC address. It actually has to make that connection. But where that's tricky is if it's an IPv6, it would also look very similar to that, except much, much, much longer. And so if you're in doubt, you can always look at it and go, all right, I know these are. So you can also then, if you wanted to, you could put those into a reader. You could go online and say, I want a MAC address decoder. You could put those in and figure out, oh, that's BioStar for the first 3. Because the first 3 of a MAC address are the manufacturer. So what is the source address? Is it an IP or MAC address? What's the destination address? We'd go in and put the same thing, but hopefully now you'd see it's a MAC address in there. The Internet Protocol version 4 part of this frame. All right. I close that one. And I open up this one. What is the destination and source address in the IP part of the frame? So in this, it says here's a source and a destination. Are those MAC addresses? So 192.168.180.103, is that a MAC address or an IP address? That's an IPv4 address. And so you could put those down. Then it's going to have you do some other questions. So you're going to start again. So here, enter the prompt command ARP-A. So I still have one open. So I can go ARP-A. And this is a list of all the addresses my computer knows the MAC address for. So I can search for it, and I can say, look at the MAC address of your default gateway that you recorded earlier. Well, over here, you recorded, this one. So you recorded an address of 82A88. 82A88. And in this case, it's a dynamic address. That's my gateway address. So I can check that. I could say, well, is that right? Let's see what happens. And sure enough, as it turns out, that is that router that we're talking about at that gateway. So that this router reads those ICMP packets and can alter them. And so that is the internet coming in to our lab. This handles all of the communications inside of here. And that's that particular router right there. So at your house, you're going to have a different value. All right. So you have a couple of questions to answer. You need to be able to use Wireshark. We're going to use it a lot in here. So if you haven't installed it, that's back as a discussion board assignment. So make sure you've done it. And I have you document it into a PowerPoint that you've installed it. You're going to then use it for this assignment. And then we're going to go on a lot of quests about how do we find out what's in there. Because not only can I find, let me find Wireshark here. So not only can I find a packet, let's just grab something at random. I can actually see exactly what the data is in that packet. In this particular case, that's the data stored in that packet. So we can actually do, there are hexadecimal editors. We can go in and read that data and manipulate it. And you can actually see exactly. So if I'm getting onto your network, sometimes I can find out information just by pulling up a packet dump. So Wireshark can be a pretty swift little way to find information about something. Because I'm recording, let's see, close that. So I'm getting all the data that this computer is seeing right here. So this, for example, we have something saying 192.168.180.233.2 255. And remember, that's that master that sends it to the entire network. Everybody listens for that one. So I could look and see what this one's all about. And that tells me all about this in particular frame. Now, in this case, it gets a little information there if you can actually sort of read some of that one. But Wireshark tells you what's going on your network. And it is a powerful, powerful tool. All right, any questions before I hit the end of the recording button for today?